Hi, everybody. So now we're going to finish up the first chapter of the course by looking at two theorems which allow us to test whether a subset of a group is a subgroup. Kind of boils down the things we need to check into a few very specific things which are more convenient for using in various other situations. So we have the general definition of a subgroup, and now we're going to try to simplify that by proving a couple of theorems which will make it easier to tell if a subset is a subgroup. So there are two theorems that we're going to look at. So let's start with the first one. And so suppose G is a group and H is a subset of G. Then H is a subgroup of G if and only if the following three properties hold. The first property says that if you have H1 and H2 in H, then their product is also in H. That's the closure property that we've seen before. The second property says that the identity element of G is an element of H. Now, we know by the definition of a subgroup that if H is a subset of G, which is also a group, so we know that H has an identity element, we don't know that it's the same as the identity element of G, and that's more or less what point 2 says. And point 3 says if H is an element of H, then H inverse is also an element of H, where H inverse is the inverse of H thought of as an element of G. So it's conceivable that you might have a big group and a small set inside it, and if you took an element of the small set, it might have a different inverse than if you thought of as an element of the big set, but that doesn't happen. Okay. So this is an if and only if theorem. So as we know, we have to prove two different things. We have to first assume that H is a subgroup and then show that these properties hold. And then we have to assume that these properties hold and show that H is a subgroup. So let's start by first assuming that H is a subgroup and showing that the three properties hold. The first property holds more or less by the definition of a subgroup. Remember that it's the operation on a subgroup is the same as the operation on G, but just using elements of H. And so the first condition holds directly from the definition of a subgroup. To see that the identity element of G belongs to H, well, we know that H is a group, so it has to have an identity element. We don't know what that identity element is, but we can call it U. And now, on the one hand, U is an element of H, so therefore it's an element of G. And so if we multiply U by the identity element of G, we have to get U back. On the other hand, U is the identity element for the subgroup H. So if we multiply U by itself, which is a product of two elements in H, we have to get U back. And as a result, we have that U times U is U and E times U is U. So E times U is equal to U times U. And if we multiply the right side of both sides of that equation by U inverse, we can cancel the U. And we get the equation E equals U. In other words, the identity element of H is the same as the identity element of G. And also, since U is an element of H, so is E. The third property says that the inverse computed as an element of H is the same as the inverse computed as an element of G. So here's big G. Here's H sitting inside it. Here's our element H. We know that H has an inverse in G, and it's going to turn out that that's the same. That inverse happens to also lie in the subgroup H. So to prove that, since big H is a group, we know that there has to be a multiplicative inverse for little h in big H. Call that element x. Then we know that hx equals E. That's the definition of an inverse, at least one side of the definition of an inverse. But this equation, hx equals E, is also true in the big group, G. And in the big group, we can multiply on the left by H inverse to get x equals H inverse E, which is H inverse since E is the identity element in G. In other words, X, which is an element of H, is equal to H inverse, which is the inverse in G. And that tells us that H inverse is actually in H. So we started out by assuming that H was a subgroup, and we proved these three properties. To finish the proof of this theorem, we need to now assume these three properties and show that H is a subgroup. That's actually easier. We already know that from because the binary operation comes from G, that it's associative. And so what do these second and third points tell us? Well, the second point tells us that the identity element of G belongs to H, and therefore H has an identity element, namely E. And the third point tells us that every element of H has an inverse, namely H inverse. And those are the three things that we need to be a group. Remember, the three axioms are associativity of the operation, existence of an identity element, and existence of inverses. And so we have all three of those things, and so we conclude that H is a subgroup. So that's the first of the two subgroup theorems. The second one simplifies matters even a little bit more. And it reduces what we have to check to really one criterion. So we assume G is a group and H is a subset of G. Then the theorem says that H is a subgroup of G if and only if it is non-empty. That's very important. So H has to have at least one element. And for all pairs of elements, G and H in H, if you multiply G times H inverse, you're still in H. So this is like a combination. I mean, we know that if you didn't have the inverse in there, it'd be just G times H. That's not quite enough, but by putting G times H inverse, you've kind of included everything you need to check. And just as a reminder here, H inverse is the inverse of H in G. So first of all, if H is a subgroup, then we already know that it has to have these properties, because since it's a subgroup, we know from our earlier result that if G and H are in H, then H inverse is also in H, and therefore GH inverse is in H. So this follows, the one direction follows from the previous result, the first subgroup theorem. So now let's assume that we have a subset with these properties, and we're going to prove that it's a subgroup. Well, the first step is to take advantage of the fact that H is a non-empty set, so we can pick an element from it. If we didn't know that H was non-empty, then we would be stuck right at the beginning. So that non-emptiness is really crucial. But since it's non-empty, it contains at least one element, call it H. And then using the property, it has to be the case that H times H inverse is equal to the identity. That has to belong to H. This is because H, we use H equals G and H equals H, and we multiply H times H inverse. That's a calculation in the group G. It's equal to the identity. And by the property, that belongs to H. So we have the identity element belongs to H. Now, if we take any element of H, call it little h, and we combine E and H to be the G and H in the property, we have that E H inverse has to belong to H. But E H inverse is equal to H inverse. So H inverse is in H. So what we've shown is that if H is an element of H, so is H inverse is an element of H. So from the point of view of the first subgroup theorem, what we've shown is points 2 and 3. We finally have to deal with point 1, that the operation is closed. So if G and H are in H, then by the previous result here, we know that H inverse is in H. And so we can take G times H inverse is in H. Because if G is in H and H inverse is in H, then using the property, that tells us that GH inverse is in H. Let me put here H is in H. That tells us that H inverse is in H. And then that tells us that GH inverse is in H. And that tells us that GH is in H. And that's property 1 of the first subgroup theorem. So we've shown all 3 properties of the first subgroup theorem, and so we conclude that H is a subgroup.